Hello everyone, welcome back. In the last couple of classes, we saw different numerical schemes. We use this forward in time and backward in space, forward in time and central in space, forward in time and forward in space. So, FTFS, FTCS and FTPS for different class of problems. We looked at the linear convection problem, nonlinear convection problem, diffusion problem, linear convection diffusion and finally, the nonlinear convection diffusion. And we looked at applications of these discretization schemes, and we found that some of these schemes are basically stable and they give you the correct solution. Schemes are sometimes diffusive, and as you increase the number of grid points or the grid size and correspondingly adjust the time step, you basically get better and better solutions. Right. So, with this understanding, we will now go to a similar thing, but for the 2D flows. Okay. I will just give you some brief idea about the 2D flows. So, all the flows that we considered in the last couple of classes are 1D flow. So, 2D is just an extension and there is nothing new there, but I will just introduce you here. So, for example, if you had this del u by del t, firstly del u by del x equal to 0, right. This was your let us say the 1D flow. So, we can have del u by del t plus c del u by del x plus c del u by del y equal to 0, right, or you can have del v by del y equal to 0, right. So, then it becomes a 2D flow. So, you have things in x also and things in y also. Okay. So, we will solve this equation today. Okay. So, the approach remains the same. So, we will use the forward in time for the time scheme, okay, and backward in space, considering that our convection speed is positive, okay, for both the spatial direction. And if you do that, so this can be written as u I plus 1 n minus u I n by delta t, and these portions can be written if you take the c as common. Okay, I am using c here considering the linear convection, but you can also have u, and if you have v, then you can v also. But if you have u and v, then you have variables u and v, then you would need two equations, right. So, here I am going to use the backward differentiating and plus u. So, I will use two indices u I j, okay, because now my grid is in both I direction and the j direction. Okay. And when you go to this delta y, then you will backward differentiating will be with respect to j. So, this is I j minus u I j minus 1 n by delta y. And if you rearrange it, it will become like this. And if you have a uniform mesh, then you can take delta x equal to delta y, and you can just extend the code that we had discussed in the last class. Okay, you just have one extra indices here. So, your array size will be now 2D, right. And let us say we take the same initial condition for both x and y. So, you have basically like this, but now it is in 2 dimension, right. So, if it is in x, so then it is basically between 0 to 0.5 you have 2, otherwise it is 1, and similarly same thing is in the y direction also, right. So, that is what we have done in both in x as well as y, and the boundary conditions also we are using that u equal to 1 at x y equal to 0 and y equal to 2. Okay. So, in both the sides, whether it is x equal to 0 and x equal to 2 and y equal to 0 and y equal to 2, we are having the same value of equal to 1 and this is 2, right. Now, it is a 2D problem. So, this is, you can just look at the code here. So, now it is a 2D array, that u is u j I, or you can write u I j, I mean it is your choice, okay. And these are just the dummy indices for the for loop, okay. And I normally use for y direction j and x direction I, okay. So, you can write c dt by dx, and this is my gradient in the I direction and this is my gradient in the j direction, right. It is the same thing that we discussed earlier, and now it is because it is a 2D flow. So, you would rather like to see a surface than a contour, Okay. So, this is how it will look like. So, you can see that between 0.5 to 1 you have the value as 2 and here also. So, because this is 2D is a 3 dimensional view. So, that is why you are having difficulty, but this is basically between 0.5 to 1 and if you just try to basically take a view in the y direction or z direction, this is how it will look. Okay. And once you solve that for a given time, like we are solving. Okay. So, this lambda is missing here, basically lambda is less than 1. Okay. Otherwise, you will not be able to solve it, it will blow up, right. So, this is how it will look like, this is the solution. So, you can see now it has traveled on the, this is the 2D view, this has traveled on the right side. So, basically the convection speed equal to 1 here and this is for 0.5 second. So, it will transfer up to 0.5. So, you can see this is I mean because of the diffusion on both the sides. Okay, you can see there is a tail coming on left and right. Okay, and this is the 3D view of the same. So, please go back and try this. So, this is just an extension of your 1D linear convection. Similarly, you can have the 2D diffusion also. In that case, you will have basically del to u by del x square plus del to u by del y square. Okay, and you can have maybe del u by del t, right. So, you can try solving this problem also in 2D. Okay. So, the idea remains the same. In this case, here you will use the forward in time and central in space, because that is a diffusion problem. Okay. And once you basically refine the grid, the same thing. Okay, so it has shifted from 0.5 to 1 because c is 1 and t is equal to t max is equal to 0.5 second, right. So, there is no difference between this one and this one, it is just that I have now refined the grid size a lot. So, now it is 0.0025 and earlier it was 0.025. Okay. So, we have refined it 10 times and you can see that now the diffusion has reduced and even the so it is supposed to be sharp corner because there is no diffusion in this particular equation, but because of the numerical diffusion we are getting some kind of a smooth surface on this side and also here and here. Okay. So, that we also saw in the 1D problem. Okay. So, now similarly you can do for 3D also. Okay. So, then in that case the indices will be I, j and k, all 3. Okay. So, it is just an extension of what we have been discussing. So, if you are interested you can go back and try the 3D problem also, because ultimately when you want to solve the Navier-Stokes equations they will be basically 3 dimensional, but at the same time you will have more variables also. So, that will be coupled equations, system of equations, you have x momentum, y momentum, z momentum separately. Okay. Now, we will go to something called implicit schemes. Okay. So, we till now when we are trying to solve a problem, what we are doing is basically on the right hand side it was always at the nth stage. So, recall the diagram. Okay, this is your x and this is your time. Okay. So, this is your spatial discretization. So, this is called the spatial discretization. Okay, that is delta x, and this is your temporal discretization, that is delta t. Okay. So, till now we have not discussed much about the temporal discretization, we have always used forward in time. Okay. There are multi-step methods also like Runge-Kutta method or Adam-Weisforth method, which can be used for the time stepping, but will not go into the detail of those discussions as of now. Okay. But let us look at that when you are trying to solve the problem which is either convection or diffusion or the convection diffusion. Okay. Can we basically do something better, so that you can increase the time step size, okay, the delta t size. Earlier it was always limited that my c delta t should be less than delta x, or basically nu delta t is less than delta x square, right. This is the convection time scale and this is the diffusion time scale, and we have said that normally the more restrictive one is the convection time scale, if the problem is involves both the convection as well as diffusion. right. So, this is an explicit approach where we this on the right hand side which is on the spatial discretization or the spatial derivative, it is always at nth stage, okay, and this is basically n plus 1 minus n, okay, by delta t, and that is how you calculate the value at n plus 1. So, right hand side is known at nth stage. So, this is my nth stage, this is next one we want to go is n plus 1th stage. So, we know all the values at nth stage and we go to the n plus 1th stage. So, if you use this explicit, this is called the explicit approach, because in the left hand side you have n plus 1 that you want to find out, and right hand side everything is known here, right. So, you can just put in the values of u I everywhere at n time step and you can get the value at n plus 1, and similarly you put the n plus 1 here, get the n plus 2 and so on and so forth. There is no matrix involved here in this particular calculation. Okay. However, what you can do is that let us take the same problem, okay, but now we will say that we will put these values also at n plus 1th stage. Okay. This may sound a bit odd at the beginning, because you do not know the value at n plus 1, right. You know the value only at n and you want to evaluate for n plus 1, right. So, how can you put the value at n plus 1? Looks like you can do that, and you can formulate the problem. Okay. So, what you can do, so del u by del t is basically u I n plus 1 minus u I n by delta t, right, and nu use the same central differentiating scheme for delta u by del x square, but at the n plus 1th time step. So, this is basically u I plus 1 n plus 1 minus 2 u I n plus 1 plus u I minus 1 n plus 1, okay, by delta x square, right. I am working for a diffusion problem, but the same thing is applicable even for your linear convection problem. Let us say if you want to do del u t plus c del u by del x equal to 0. So, here you can do u I n plus 1 minus u I n by delta t plus c, and if you are using backward differentiating scheme, this is u I n plus 1 minus u I minus 1 n plus 1 by delta x. Okay. So, the only difference from the explicit scheme is that now all these values on the spatial derivative are also available at n plus 1. Okay. So, how do we solve this problem? Okay. So, let us try to formulate and put this n plus 1 on the left and n minus n at the right. Okay. So, you can write it as okay, u I n plus 1, just a second. Okay. So, u I n plus 1 minus u I n, and I will use alpha as my symbol for nu delta t by del x square. You can also use lambda if you want. In the last class we have used lambda, but it is basically the diffusion based Courant number. Okay. Will become alpha u I plus 1 n plus 1 minus 2 u I n plus 1 and plus u I minus 1 n plus 1, right. Now, we will put all the n plus 1 terms on the left side and n term on the right side. So, you can write it like minus alpha u I minus 1 n plus 1, and this will go on the left side. So, this will become 2 alpha. So, plus, and there is 1 here. So, 1 plus 2 alpha u I n plus 1 and minus alpha u I minus 1 and n plus 1, right, would be will be equal to u I n, right. Now, you can quickly see that if we have formulated the problem in an implicit way. So, what do I mean by implicit way is that you have a matrix, okay, which has basically u 1 n plus 1, u 2 n plus 1 and u 3 n plus 1 and so on and so forth to let us say u n x n plus 1, right, or u I n plus 1, and there is a matrix which multiplies here, which contains the term of 1 plus 2 alpha minus alpha minus alpha 1 plus 2 alpha minus alpha and so on and so forth, right. And this will multiply some matrix here. Okay, let us say this is A x and this will be another matrix, and this is basically u 1 n, u 2 n, u 3 n. So, in this case it is an identity matrix. Okay. All others are 0, okay, in this particular case, and this is u n x n, right. So, all the n plus 1 time steps are on the left and n time steps on the right. So, if you can somehow invert this matrix, which is for a smaller problem it is very easy, but for a big problem you need to have some kind of algorithm to basically find the approximation of the inversion, because inversion is a very costly operation, matrix inversion. Imagine that this is a million cross million matrix, right, and you want to invert that, right. So, in those cases you need to make use of some kind of algorithms like Thomas algorithm, which gives you a good approximation to the inversion. Okay. This is called implicit, like we discussed for the compact scheme also, we had this kind of matrix formation in the compact scheme also. So, basically this is an implicit problem, and you get all these n plus 1 at the same time. Okay. Once you invert the matrix, multiply with the current time step, and you can get all the n plus 1 values at the same time. Okay. Unlike in the explicit approach, where you get first you will do in a sequential way u 1, u 2, u 3 and all the way to u n x, right. So, here you can get everything at the same time, but you have to invert this matrix which I have written as the A matrix. Okay. So, this approach is called the implicit approach, and the same thing shown here. Okay. And if you will just let us say 4 points. Okay. So, 1, 2, 3 and 4, let us say I have a grid which has got only 4 points. So, the first one and the last one will of course be the boundary points. So, you need to put the boundary conditions, right. So, let us assume that okay, at n time step I know the value, and this boundary conditions are always 0. So, boundary conditions are always 0 regardless of the time, okay, unless it is a time varying boundary condition. In most cases the boundary conditions do not change with time. Okay. So, this is my first one is 0 and last one is 0, and for 2 you want to write your implicit formulation. So, this is minus alpha u 1 n plus 1, 1 plus 2 alpha, your I equal to 2. So, this is u 2 n plus 1. So, remember this is minus alpha u I minus 1 n plus 1 plus 1 plus 2 alpha u I n plus 1 minus alpha u I plus 1 n plus 1 is equal to u I n, right. So, put I equal to 2 and you will get this formula, put I equal to 3 and you will get this one, right. And if you collect it together, you will get the matrix that we have discussed earlier. Okay. And these two things that you are seeing is because of the boundary condition. Okay. You might make a matrix which is basically n x minus 2 also, where you can remove the boundary conditions and just solve for this matrix, which is the size of that matrix is n x minus 2 comma n x minus 2, right. So, where you will not consider 1 and n, but only the interior points, or you can basically formulate a matrix where you put the boundary points also in the matrix and solve for the entire n x, okay, the total number of grid points. Okay. So, this is the matrix representation of the earlier equation. This is A x equal to b, and you want to get x, the x will be A inverse b. Okay. If you are using MATLAB, so this will be basically A as b, like that, or you can have p inverse or inverse of A. There are many ways to do that. You can do A and v A into b, okay, or there is a p and v A into b. Okay. So, normally inversion operation, if possible, you should go with that, else in some cases the matrices the condition numbers are very high. In that case you can go for the P inverse, okay. Or if the matrix inversion creates some difficulty in the direct operation. Okay. So, similarly there is another approach which is called the Crank-Nicholson method. Okay. This is a very popular approach. Okay. Before we go there, why did we go for the implicit scheme? Okay. Explicit scheme was working fine, So, what was the need to go for the implicit scheme? And the reason for that is that in the explicit scheme you have a limited I mean your restriction on the delta t, right. So, as we have been discussing, the jump should not be more than the basically the grid cell size, okay. And that is what limits your delta t, the time step, right. We will see shortly that when you use the implicit scheme, okay, that means your right hand side is also available at n plus 1 while calculating, then the restriction on delta t goes away, okay. So, you can use a higher delta t. That is a very big thing in CFD, okay. All the research that is going on is basically how to basically formulate a scheme or get a scheme which can allow you higher allowable delta t while also preserving the accuracy of the scheme, okay, and while making sure that the solution does not blow up, okay. So, if you can devise a scheme which allows you higher delta t, okay, that is a very good thing to do, but you have to make sure that solution does not blow up and it remains it gives you decent accuracy. So, the implicit problem, as I told you earlier also, it is very useful when you want to just get the mean flow. For example, in the RANS simulation, Reynolds average Navier-Stokes simulation. So, for example, you started with some initial condition, okay. This is your first point and you want to go here, okay. So, if you let us say you use the explicit approach, this probably go like this, okay. This is let us say your explicit approach, where you are basically honoring the accuracy at every time step and getting from this point to this point, okay. But in the case of RANS simulation, your interest is this is let us say the number of iterations, okay. So, your interest is basically to get the final solution regardless of the way you choose, okay. So, if you can get a value, get an approach which can give you this convergence very fast, okay, by increasing the delta t, and of course, the solutions, intermediate solutions are not actual, not correct, okay, but you are getting the final solution which is same as your solution that you would be getting from the explicit solution. So, then it is a you are saving a lot of conversational time, okay. So, this is only possible when you use the implicit time stepping, okay. So, despite of the fact that you are now creating a matrix and which is becoming slightly more expensive than your explicit approach, the implicit scheme allows you to use much higher time step than the explicit scheme. Of course, there are physical consideration, although we will see that implicit schemes are unconditionally stable. That means that regardless of whatever time step you use, it will not blow up, right. But there are physical consideration, whether what is the delta t we should be using, what is the maximum Courant number that should go, right. But typically, for example, in explicit, if you are limited by Courant number which is less than 1, okay, you can easily go in for the implicit scheme, for example, Courant number less than 5 or less than 10 and so on and so forth, okay. So, this is the beauty of the implicit scheme, that it gives you the convergence faster. Of course, if you want to get a time accurate solution at every time step, okay, you should not be using the Courant number very high, otherwise the accuracy with the time will go down, okay. So, similar to the implicit approach that we had in time, you can also have a scheme called Crank-Nicholson scheme. So, what it does in this Crank-Nicholson scheme, you basically take the average of the nth time step. So, this is my nth time step and this is my n plus 1 time step, right. So, we will take the average of these two things on the right hand side. So, you can see it here. So, what we have done, we have taken 1 by 2 of values at nth time step, okay, and then half of n plus 1 time step, okay. And if you reorganize that, take that nu delta t by del x square is equal to alpha, right. So, this will become u I n plus 1 minus u I n, and they take this 2 on the left hand side, this will become 2 will be alpha u I plus 1 n minus 2 u I n plus u I minus 1 n, and plus you will have u I plus 1 n plus 1 minus 2 u I n plus 1, and plus u I minus 1 n plus 1, right. You collect all the n plus 1 term on the left. Okay. So, these are the n plus 1 terms, okay, they will go on the left and all the n terms on the right. So, you can write it minus alpha u I plus 1 n plus 1, okay, we will write the I minus 1 term first, this I minus 1, okay, plus 2 1 plus alpha, this negative term will become positive and multiply by alpha, okay, that will become u I n plus 1 and minus alpha u I minus 1 n plus 1, and on the right hand side you can write it as, so this will become alpha u I minus 1 n and plus this will become positive plus 2 1 minus alpha, okay, u I n plus alpha u I plus 1 n. Okay. You can write it in the matrix form, okay, which is shown here. Okay. So, this is your n plus 1 and this is your n, and your matrix looks like this. Of course, the top and bottom I have kept as the boundary condition. So, these indices that you see 1 and 1, they will be replaced, that depends on the what kind of boundary condition that you want to use. Okay. But the internal matrix structure will be the tri-diagonal structure, where there will be alpha term here on the off diagonal terms, on the diagonal terms will be 2 1 plus alpha on the left hand side. So, this is your matrix A, and on the right hand side you will have 2 1 minus alpha in the diagonal terms and alpha in the off diagonal terms. Okay. So, both are basically tri-diagonal matrices. Okay. You can write a little code to basically solve this problem. Okay. So, here for example, E is equal to 1 sin x minus 1, and then you are putting minus alpha 2 1 plus alpha and minus alpha on the off diagonal terms and create this matrix using SPDIX. Okay. And similarly, for the right hand side, this is alpha 2 1 minus alpha and alpha, and you are creating a matrix on the right hand side. You can apply the BC that you have, okay, and use the Crank-Nicholson method, which is basically, okay, this will be basically u is equal to A inverse B, okay, and the older time step. Okay. So, this is what the value will be. Look at the matrix on the left side, this is your u at older time step u n, this is B, and let us say this is your u n plus 1. Okay. So, u n plus 1 will be A inverse B into u n, right, or in the matrix it will be A B u n, right. So, the same thing you can write it here and solve it. I will show you one example here. Okay. So, this is the extreme case that we had considered for the diffusion scheme, okay, where nu was 0.243, recall that we have discussed in the last class. So, that gives you the lambda or the alpha value, okay, as 0.5062, and we saw that for the explicit scheme it basically blows up. Okay. You can see it here, this is the explicit scheme, forward in time and center in space. Okay. Now, we are solving the same problem using the implicit scheme, and you can see that you are getting the solution which is not blowing up, right. You increase the value of nu or decrease the value of delta t, still it will work. Okay. So, this is the beauty of the implicit scheme, that it allows you the a higher delta t compared to the explicit scheme. Okay. So, before I close the class, I just want to introduce some more schemes, and we will discuss about this scheme in the next class. Okay. For example, there are many different schemes which have been built over the time. Okay. So, right now we have taken the average of n and n plus 1 in the Crank-Nicholson. There is a scheme called leapfrog scheme, where what we do, we will use a central in time and central in space. Okay. Similarly, you have the Lack-Frederick scheme, where it is the forward in time and central in space, but the central part that, so this is all shown for the convection problem. Okay. Del u by del t plus C del u by del x equal to 0. Okay. So, we have taken the average on so on this I plus 1 and I minus 1 when you are trying to get the central in space. Similarly, you have the Lax Von Trapp scheme, which is also the central differentiating scheme in the space, but you have got the numerical diffusion as well. Okay. So, we will discuss about these schemes in the future classes. We will stop here and we will meet in the next class. Thank you.